This lesson involves solving systems of equations by elimination. As way of review, I want to talk about systems of equations, what they are, and what the solution to a system of equation looks like. At this point, we've already taken a look at systems of equations, what they are, and how to solve them graphically. As an example, that's what we have right here. What we've done is we've graphed both of the equations. We've graphed y equals -1/2 x plus 4. That's the positively sloped graph over here on our coordinate plane. And then we also have graphed, or sorry, the negatively sloped. We also graphed y equals 2x minus 1 on our coordinate plane over here. So this being the y equals 2x minus 1 equation, this being the y equals -1/2 x plus 4 equation. And we've seen already that the solution to a system of equations is the coordinate point that works in both equations. Graphically speaking, that's the point at which the two graphs intersect. Here, they're intersecting at the point 2, 3. So we would say that the point 2, 3 is the solution to this system of equations because it's the one coordinate point that works in both both equations in our system at the same time. However, we don't want to have to continue to rely on our ability to graph systems of equations in order to figure out the solution to the system of equations. We want to be able to do this algebraically. Okay. With systems of linear equations, there's two algebraic methods that are helpful to us. So it says here we want a way to solve systems of equations algebraically so we don't have to rely on graphing to find our solutions. Well, the two methods that we're going to be learning how to solve a system of equations algebraically are elimination and substitution. This lesson we're going to focus on elimination. The next lesson we will focus on substitution. Okay, so these are algebraic methods, meaning no graphing. It is simple algebraic manipulation that gets us at the solution to our system of equations. Now for elimination, there's a couple things necessary to get set up to make elimination work. So let's work through those couple steps with an example that we have here below. So elimination steps. So we've got our system of equations right here, the 3x minus 2y equals -9 and 10y equals -5x minus 15. Now the first step in solving a system of equation through elimination is that you want both equations, or is that both equations must be written in the same term order. In the same term order. What that means is the terms of each equation are in the same order. So for instance, this top equation is the x term, the y term equals the constant term. However, down here we have the y term equals the x term times the constant term. You can see that the terms are in different orders and in just different locations in our equation. The best bet for solving by elimination is to just put both equations in standard form. We know slope-intercept form of an equation, that's y equals mx plus b. We know this form really well. Standard form we've seen before, not as much as slope-intercept, but it's ax plus by is equal to c. Standard form. This is the form that it's useful to put our equations in to complete elimination. So that's what we're going to do. We'll see already that this top equation here is already in standard form. It's the x term, y term equals a constant, and that's exactly what standard form is. The x term times the y, and then the y term equals the constant. However, this bottom equation here is not in standard form. The one term that's not in place is this x term here. So this x term here, we need to move to the other side of the equation. To do that, I'm going to add 5x to both sides. Now we want to write it as x term, y term equals constant. So keeping my 3x minus 2y is equal to negative 9, I now have on my bottom equation, because I added 5x to the left-hand side, I have 5x plus 10y is equal to negative 15. You see now that by adding the 5x to both sides, I've put that bottom equation in my system of equations into standard form. Now, as you notice, both equations are in the same term order. In other words, I have my x's listed first, my y's listed second, and my constants listed third after the equal sign. Okay. Now that we have that, you can see that we have that down here. I've rewritten what we've got down here. We can now do the second step. Okay. The second step in setting an equation up or system of equations up for elimination is that one of the variables, right here, one of the variable pairs must have opposite coefficients. Opposites meaning positive, negative. Positive, negative. Okay. So what we mean by positive, negative is that they have to have the same value coefficient, but one needs to be positive, the other needs to be negative. That means opposites. So we can look at the variable pairs. We can look at the x's here. 3 and 5, definitely not opposites. Now we can look at the y variable. The coefficients there, negative 2 and 10. One is positive and one is negative, but it's negative 2 and positive 10, not opposites. Well, the second statement here shows how we can achieve this. It says to achieve this, it may be necessary to multiply one or both of the equations by a constant. Okay, so what we're going to do is we're going to either multiply just one or both the equations by a constant to make one of the variable pairs have opposite coefficients. Okay, so what I see is this. I see that if I multiply this negative 2 by a 5, that it'll turn into a negative 10, which will be an opposite of 10. So that's what I'm going to do. I'm going to take this top equation and I'm going to multiply the entire equation by 2. You can't just multiply one term. You have to multiply the entire equation by 2 in order to make sure you're maintaining balance in your equation. So 2 times 3x is 6x. 2 times negative 2y. Oh, we're not multiplying by 2, we're multiplying by 5, aren't we? So times 5. Okay, so 5x times 3x is 15x. 5 times negative 2y is negative 10y equals 5 times negative 9 is negative 45. Okay. So we've multiplied everything by 5, not 2, sorry about that. Multiply everything by 5 in order to make this negative 2 into a negative 10 so that it's an opposite with the other 10 that's in front of the other y, the other coefficient of the y. And then we can keep our other equation of 5x plus 10y is equal to negative 15. So we've achieved the situation that we wanted, that one of our variable pairs have opposite coefficients. The one we achieved this with was the y's. We have opposite coefficients here of 10 and negative 10. So the question now is, why did we do this? Why in the world did we do this? Well, this set us up for the process of elimination. Okay? The process of elimination involves adding the equations together. Okay? We do this by adding the like terms from each equation together. So you can see how lining things up allows us to add the like terms of each equation together. because the x's are lined up, and 15x plus 5x is 20x. Okay? Now we move over to the y's. And here's the reason why we multiplied that top equation by 5. Because now that I have opposite coefficients on my y's, when I add the y's together, negative 10y plus 10y, it equals 0. It goes away. They eliminate each other. And that's why this is called elimination. And this equals negative 45 plus negative 15, which is negative 60. So by adding these together after we've accomplished the first two steps, we've essentially eliminated one of our variables from this new equation that we have, which means we can now take the 20x equals negative 60 and solve for x. To do that, I'm going to divide by 20, and I'm getting that x is equal to negative 3. X is equal to negative 3. So what we've accomplished here is that we've actually found or solved half of the system of equations. We know from graphing that the solution to a system of equations is a coordinate point, an xy coordinate point. Okay? So we have half of that done. What we can do now that we have the x is we can pick and choose any of the original equations we want. I'm going to pick the top one. I'm going to go 15x minus 10y is equal to negative 45. And I can take this x equals negative 3 that I've already figured out, already solved for that x, and plug it into the x of that equation, which means that I will only have y left, and I can solve for that. So we end up with 15 times negative 3 minus 10y is equal to negative 45. So that is negative 45, that's the 15 times negative 3, minus 10y is equal to negative 45. Solving for y, I'm going to get rid of anything that can be added or subtracted away from the left-hand side. I'm going to add 45 to both sides. That produces negative 10y is equal to 0. So negative 45 plus 45 is 0. Now I'm going to multiply or divide away anything that I need to from the y. So divide by negative 10, divide by negative 10. And that produces y equals 0 over negative 10 is 0. So y equals 0. I now have both the x and y coordinate that represent the solution to my system of equations. But what we want to do is make sure that we write our solutions as coordinate points. So the coordinate point that is the solution to this system of equations is the coordinate point negative 3, 0. So negative 3, 0 is the solution to our system of equations. If we were to graph the two equations in our system of equations, negative 3, 0 is the location at which those 2 points would intersect each other.